Once again, I'd like to thank Sarah and also Pacific Life for inviting me up here. It's very nice occasion. And I should say I learned many things yesterday. One of the things I learned was ppm has another meaning other than parts per million, which is what I usually use it for. It's porpoises per minute. Very good. So I'm going to talk mainly about sardine, but I'll also mention a little bit of anchovies, mackerel, albacore, and squid. And I'm going to focus on things that have been near to me, which I know most about. Let's see what happens. Is it the top ones you think? Okay, good. And some of this will be a reiteration of what's already been said, but that's okay. The scales of variability are shown here, going from daily up to secular meaning 100 years. And if one thinks about climate change and climate variability, I put those near the top here. Let me first say that ENSO is about 3 to 7 years, the El Nino Southern Oscillation. Climate variability is in the lexicon right now referring to natural variability and variability basically below the secular scale, I would say. And climate change includes all of these scales. And so there's effects of climate change, which itself has a scale that's certainly beyond 100 years, but it affects what happens at a daily, interannual, and so on basis. And so what I'd like to do is focus on two of these scales. One is ENSO and the other is decadal right now. You've already seen from Elliott an image of the multivariate ENSO index. It's an index of 6 variables: sea surface temperature, cloudiness, sea level pressure, a variety of other things in the ENSO region and the equator. And at the top is a difference between sea level pressure between Tahiti and Darwin, which indexes the flow of winds, the geostrophic flow, which also is a measure. And I reverse the values there. But you can see these are both measures of variability in the ENSO scale that affect what happens here. And so what happens is the equator, these variations occur, and then they propagate up the coast, both north and south, to Peru, and then up to where El Nino was coined. In Christchild, and then north to our region through Rossby waves, and our waters become warmer in El Nino, cooler in La Nina. What I thought I'd show you are some data for sardine, anchovy, and mackerel that are the spawning areas that are collected with what's called the continuous underway fish egg sampler. If you just Google my name, you'll get my website. You can go to the CUFS data, and you can get to the website that has these plots on it right here for the last 14 years. These are collected by the National Marine Fisheries Service, the La Jolla Laboratory. Ed Weber and Sam McClatchy are in charge of these right now. But they're wonderful maps. In the background are sea surface temperature, and on the left-hand side are the abundance of sardine eggs, in the middle anchovy eggs, and to the right-hand side jack mackerel eggs. And so this is from an El Nino period, 1998. You can see the multivariate ENSO index on top there. Strong El Nino, very strong one actually. And you can see that the sardine eggs are compressed to the shore. They're right up against the beach here basically. This is the same thing that happens in Peru during El Nino. The anchoveta are pressed right up near the shore. And you can see anchovy similarly here, and jack mackerel almost gone. So the next year was a La Nina year, a strong La Nina. You can go over to the right in the top and see that. And look where the sardine eggs are now. They're dispersed widely over this area. The water's cooler. And you see more jack mackerel eggs, and actually anchovy are a little bit further out. But what I'd like to emphasize is that the sardine distribution varies on an interannual basis, especially with La Nina, El Nino, in a very dramatic fashion. And you can see this if you go to the website and go through all of the years. These now are prey of marine mammals, and I think that no doubt they have an influence on the feeding of those. So I'm just going to go to 2 more years, 2009 I believe this is, another La Nina year. In fact, the next one is going to be a slightly not La Nina year also, or a cold year. And you can see the sardine eggs are distributed fairly broadly. And then last year, 2 years ago, 2010, now they're distributed somewhat farther north, but still broadly offshore. So this is how sardine varies on an interannual basis with El Nino and La Nina. If we then go to the decadal scale. This is the PDO, or the Pacific Decadal Oscillation. It's a measure of the sea surface temperature broadly over the North Pacific. It's the first principal component of that variability. It's the main mode of variation. The second principal component is something called the North Pacific Gyre Oscillation, the NPGO. But the PDO is the one I'll talk about right now. And you can see there's a lot of, these are monthly values, there's a lot of variability here in the monthly scale, but there's a broad curve that you could draw through these that has this period of about 50 to 70 years. And this is anchovy catch in blue, sardine catch in blue and anchovy catch in red. I could plot the spawning spot biomass, but there aren't as many data for those, but they show broadly the same variability, except at the start of the sardine fishery at its inception. But basically, sardine were big through the war, the Second World War. They were fished strongly, even as they started to decline in recruitment. And then they crashed twice, actually, and finally fell down about 1950 to the low level that they existed at during the cold period when anchovy was abundant. The things to note here are that there was a strong crash of sardine, that anchovy became abundant, but it never rose to the level of sardine in terms of catch. And in most of these systems around the world, the Humboldt, the Benguela, the Canary Current, Curacao, Washoe, and our current here, there's one species that dominates. It's either sardine or anchovy, not both. And so the characteristic here is that this is sardine territory. And then sardine has come back since about the 1980s. And what I'd like to do is explain why this might be, or offer a hypothesis. And so plotted again is the NP, or the PDO at the top here, warm period, cold period, warm period. And if one looks to see when these populations change, they were due to both fishing and climate, no doubt, that the recruitment started to drop dramatically for sardine when the PDO changed from a warm to a cold period, and vice versa. When it changed from cold to warm, the recruitment for sardine started to increase once again. The reasons for this became a little bit clearer when a student working with me, Ryan Rikaszewski, it's 99% good work, looked into the fine scale distribution of the spawning of sardine as well as anchovy, but especially sardine, and discovered that they spawn where the wind stress curl is very high. So the curl of the wind stress comes from this gradient in winds moving offshore. As you move offshore like this and the winds increase further offshore, this causes Ekman drift, which is higher here than here. It causes water to be brought up, and so this is what's called curl-driven upwelling, and it's in contrast to the coastal wind-driven upwelling to the right. And what Ryan shows here is in the left, the sardine thrive in this curl-driven upwelling environment, whereas anchovy are more apt to be in the coastal wind-driven upwelling period. And this has to do with the rates of upwelling. It's very fast near shore in the coastal wind-driven upwelling, and this has to do then with, this causes the plankton to be rather large, whereas offshore the plankton are small. Sardine have small gill rakers, or small mesh size in their gill rakers, and anchovy have large mesh size, and so they're adapted to these two environments. And if one looks at the production of the sardine population, it basically varies well. More variation in it can be explained by variation in the curl-driven upwelling than in the coastal wind-driven upwelling. So this is one explanation that's been offered for the variation in the sardine abundance over time. Now, what's the sardine doing right now? These are statistics from one of the most recent stock assessments, Kevin Hill et al. At the Southwest Center. And these are every 6-month landings of sardine. And you can see they're starting to drop now for the last 4 years or so. And shown here are those same data in the bars, but also recruitments in the bars, the young fish entering the fish stock. The ratio of recruitment to biomass, you get an index of how healthy the population is, what its propensity to increase is. And I've done that here. And so that on the left, back in the 50s, there's a recruitment for biomass, which had a value of about 1 in these units. And you can see it's been declining in recent years on the right. And so these are the declines here. What I meant to put another thing up here also, but at the bottom is the Pacific Decadal Oscillation in the background, and the declines of the sardine are shown here. And what you can see is when the sardine crashed right here, it went from high PDO values to low values here. And you can see there's been a change like this over time here. And so it looks to us like the sardine population is on its way down again right now. Now let me just finish by saying a few things about climate change. The four major effects are going to be warming, rising, souring, and suffocation, we would say. And let me just say two things. One is habitat compression. Tony just talked about oxygen. So oxygen is being depleted in the ocean as predicted in global climate models. And pelagic species are being limited to a smaller volume of water, and therefore this might affect their interactions, increase the encounters. And this might go so far as to, well, you can infer what that might mean. And these are data from a paper by Steve Brokrad et al. Up at the Pacific Center up in Monterey. And they show the shoaling of the, it actually shows actually the concentration of oxygen change per year at 50 meters depth. And it's occurring more rapidly near shore than offshore. Down on the right-hand side is the plot of oxygen concentration at that red dot station. It's declining over time at 50 meters, and similar data exists for other places. And this is the shoaling of a boundary that is where of hypoxia. Below that, it's at deeper depths, it's less than 1.2 mils per liter oxygen. Above that, it's greater than that. And so this region in which it's habitable for fish, depending on what their sensitivity to oxygen is being slowly compressed due to the rising of this layer, or this boundary of low oxygen to high oxygen. Phenological changes will be important. Phenology is the timing of biological events, and so when the water warms or other things happen, various aspects of the system might change differently, and hence their interactions might change. And this is work of a graduate student, Rebecca Ash, in my lab, and what it shows is that over the 50-year period or 60-year period of the Cal coffee collection, that many of the species, 43 species, are spawning earlier than they were back at the early part of this time series. And if one looks at this in a slightly different way, the same trend exists. So just to repeat then, or to cap up, that there's variations in all of these scales, and that climate variability is important. It's apparent in the distribution of sardine and anchovy, prey of the marine mammals, and in climate change is very likely to have an effect on these distributions in the future. I think that's it. I have two more slides, but I think I'm going to forego them, so sorry.